1 teaspoon of Neutron Star material weighs 4 billion tons. That single fact rewrites everything you think you know about matter, gravity, and the fate of stars. Welcome to the most extreme addresses in the known universe. Chapter 1. The Death of a Star. A massive star burns for millions of years by fusing hydrogen into helium, helium into carbon, carbon into heavier and heavier elements, all the way up to iron. Iron is the dead end. Fusing iron costs more energy than it releases, so the core stops fighting gravity and collapses in less than a second. The outer layers fall inward, rebound off the rigid core, and explode outward in a supernova, briefly outshining an entire galaxy of 400 billion stars. What gets left behind depends entirely on how massive the original star was. Chapter 2. The Neutron Star. For stars roughly 8 to 20 times the mass of our Sun, the leftover core becomes a neutron star. Gravity crushes protons and electrons together into neutrons, packing a mass greater than our entire Sun into a sphere just 20 kilometers across. That is why 1 teaspoon of its material weighs 4 billion tons. The surface gravity is 200 billion times stronger than what you feel standing on Earth. Neutron stars also spin, and they spin fast. The fastest known, a pulsar called PSR J1748-2446 AD, rotates 716 times every single second. At its equator, material is moving at nearly a quarter of the speed of light. A lighthouse beam of radiation sweeps across the galaxy with clockwork precision, which is why astronomers use pulsars as the most accurate natural clocks in existence. Chapter 3. The Black Hole. Push the collapsing core beyond about 3 solar masses and neutron pressure is not enough. Gravity wins completely. The core shrinks past every known threshold and becomes a black hole, a region where space-time curves so severely that not even light can escape. The boundary of no return is called the event horizon. For a black hole 10 times the mass of our Sun, that horizon is only 30 kilometers wide. But black holes scale. At the center of our own Milky Way sits Sagittarius A star, a supermassive black hole 4 million times the mass of our Sun. Its event horizon is roughly the diameter of Mercury's orbit. And that is modest. The black hole at the heart of galaxy Messier 87 is 6.5 billion solar masses. The image of its shadow, captured in 2019, was the first direct photograph ever taken of a black hole. Chapter 4. Exotic cousins. Between neutron stars and black holes, theorists have proposed even stranger objects. Quark stars, where neutrons themselves are crushed into their constituent quarks. Magnetars, a subclass of neutron star with magnetic fields 1,000 trillion times stronger than Earth's. Strong enough that at half the distance from Earth to the Moon, the field would erase every credit card and distort the electron orbitals of your atoms. In 2004, a magnetar called SGR 1806-20 released more energy in 1/10 of a second than our Sun emits in 100,000 years. The pulse reached Earth from 50,000 light-years away and still measurably disturbed our ionosphere. Chapter 5. Collisions and gravity waves. Neutron stars do not always die alone. When two orbit each other and spiral inward, they merge in an event called a kilonova. In 2017, gravitational wave detectors on Earth felt the ripple from such a merger 130 million light-years away. The collision forged gold, platinum, and uranium, scattering them across space. The gold in a ring on your finger was almost certainly born in a neutron star collision billions of years ago. These mergers may also produce the heaviest neutron stars, or tip directly into black holes, blurring the line between the two most extreme objects we know. Chapter 6. The Open Question. Scientists still do not know the exact equation of state inside a neutron star, the precise relationship between its pressure and density at the core. That mystery determines whether strange quark matter exists, whether neutron stars have solid quark cores, and exactly where the line is drawn between neutron star and black hole. Every new gravitational wave detection from a merger adds a data point. Every pulsar timing measurement narrows the uncertainty. The universe is running the experiment for us in real time. What is the densest or strangest natural object you had ever heard of before today? 1 teaspoon of neutron star material weighing 4 billion tons. That is the universe setting the bar, and it belongs here at the Curio Cabinet.